Module 7 Investigation 6 Transformations of the Sine function. A Ferris wheel has a radius of 52 feet and the horizontal diameter is located 58 feet above the ground. So I kind of want to draw this. So here's this blue line will be the ground. Then if we go 58 feet above, we get to the horizontal diameter, so that would actually be up here. So this is 58 feet, and then our radius is 52 feet. If the Ferris wheel rotates at a constant rate of 1/4 radian per minute, how many minutes does it take for the Ferris wheel to make one full revolution? Well, we know that there are 2 pi radians in one complete revolution. Now it's going to take us a minute to rotate 1/4 of a radian. So 1/4 radian per minute. So how many minutes will it take us? How many minutes x will it take us to go 2 pi radians? I don't usually use proportions like this, but here it just seemed natural. So we can cross multiply and have x times 1/4 equals 2 pi. Multiply by 4 on both sides, x is 8 pi. So it takes 8 pi minutes for one full revolution. And that is 25.13 minutes. Define a function g to represent the distance in feet of a Ferris wheel bucket above the ground as a function of the number of seconds t since the Ferris wheel began rotating from the 3 o'clock position. Assume the Ferris wheel rotates at a constant rate of 1/4 radian per minute. Okay, so my function g will represent the distance since we started from the 3 o'clock position. Notice that we have an initial height of 58 feet. So sine of 0 is 0, but we have to start out with 58. And we're going to add on whichever vertical distance that we travel through, or that whatever vertical distance the Ferris wheel car is at. So if the car is up here, then we have this vertical distance. It's going to be added on to 58. So we're just going to add on 52 sine of, it would be theta, but since we want this function in terms of time, we know that if time is in seconds, let's see, so what do we have? We have a few things here. First of all, the theta is 1/4 radian per minute. So if we want to know how many radians we've traveled through, just take the number of minutes and multiply by the time. Here, this says as a function of the number of seconds t. I think that we could just change that to minutes and make our lives a little bit easier. So that is, let's see, so then I don't think we have any problems. This is 0.25 t, and so that's what we can put here. Now suppose the Ferris wheel rotates at a constant rate of 3 radians per minute. Okay, so then the number of radians would be 3 times the number of minutes. How many minutes will it take the Ferris wheel to make one full revolution? So one full revolution is 2 pi radians. But if we're doing 3 radians per minute, we can divide 2 pi by 3. So it's going to take 2 pi over 3 minutes, which is about 2.09 minutes to make one full revolution. What might the function h of t equals sine of 2t represent in the situation? Well, know that we have to input a value of radians into the sine function. So 2t, there are the 2 in the 2t, means that the Ferris wheel would travel through 2 radians each minute. Okay, so why is the sine function useful? What 2 quantities does the sine function relate? Let's tackle the second question first. The sine function relates the measure of, let's see, an angle to a vertical distance from the horizontal diameter to a point in circular motion. It doesn't have to be circular motion necessarily. Could just be it could be something else. Let me read what the book wrote. The sine function is useful for modeling periodic behavior, including circular motion. The input of the sine function is an angle measure, and the output of the sine function is a vertical distance measured in number of radii, or the number of radius lengths. So because we're going to repeat our height as we move around the circle, our total height, the sine function is useful because it's a periodic function. It repeats. There's lots of behavior like swinging pendulums and other things that could be described using either a sine or a cosine function. What is the period of the function f defined by f of theta equals sine theta? What does the period of f represent? So I know that one's 2 pi. That's just our unit circle, like the vertical distance on the unit circle. You can think about for that whole function to make one complete revolution, we have to go all the way around the unit circle. So the period would be 2 pi radians. As the angle measured changes by 2 pi radians, the output of the sine function, the number of radius lengths in those vertical distances, would begin to repeat also. And the book says the period of f is 2 pi. The period represents the smallest input interval corresponding to the argument of f, varying by 2 pi, and the output of the sine function completing a cycle of values. It's interesting they noticed it's the smallest interval because that function repeats forever. We could say that it repeats over the interval from 0 to 6 pi, but the smallest interval of which the cycle of output values repeats is 2 pi radians. A bike is on the rack at a bike shop so that the technician can turn the pedal with his hands, causing the bike's wheel to rotate as he turns the pedal. For every 1 radian that the technician rotates the pedal counterclockwise, the wheel spins 4 radians counterclockwise. Make an illustration of the circular turning path of the pedal and the circular turning path of the back tire to depict their relative sizes. So here's my bicycle tire, and then I assume the pedal is like if it was a bicycle, we'd have one tire and then we'd have another tire, then the pedals would be somewhere in the middle. So I'm assuming that the pedal is like over here. And there's the circular motion of the pedal. What's interesting is that if we say rotate the pedal just 1 radian, so that there's 1 radius length swept out, then 4 radians get swept out here with the tire, so it turns 4 radius lengths, or 4 radii. It's kind of interesting. Suppose the pedal and a tire valve on the wheel both start at the 3 o'clock positions on their respective circle of motion. So here's the tire valve right here, and then here is my pedal right here, I guess. I'm going to put it right here. Let's see, so the tire valve is 12.5 inches from the center of the wheel's rotation. That means that the radius of this circle is 12.5. Let theta be the angle that the pedal sweeps counterclockwise from the 3 o'clock position. So our angle theta will be right here as the pedal moves around. Illustrate the location. Okay, I think we've done that. Write a function f that outputs the horizontal distance of the pedal from the vertical diameter in radius lengths as the pedal rotate theta radians. So recall that the function that gives the horizontal distance is the cosine function. So my first guess is that we just need f of theta equals cosine of theta. And that will tell us if we, let's see, rotate some angle theta here, it'll tell us this yellow horizontal distance that we've come out in terms of the number of radians in radius lengths. Notice that we're asked for radius lengths, so this works. If we were asked to inches, we'd have to multiply by the radius of this circle, but we don't know what that is. Write an expression to define the angle rotation of the tire valve in terms of the angle of rotation of the pedal theta. So let me just call the angle of the rotation of the tire valve alpha. So alpha is always 4 times as much as theta. So use your expression in part D to write a function g that outputs the horizontal distance of the tire valve from the wheel's vertical diameter in radius lengths if the input quantity is theta. So if the input quantity is theta, it'll have to be 4 theta because we really want cosine of alpha, but alpha equals 4 theta. What interval of theta will cause the pedal to make a full rotation? What interval of theta will cause the tire valve to make a full rotation? Explain your reasoning. Okay, so the pedal will make a full rotation after 2 pi radians, just like normal. So theta will travel, or the interval will be from 0 to 2 pi. But for the tire valve, that angle we're saying is alpha, and alpha is equal to 4 theta. So for alpha, the interval will be from 0 to I don't know, what would that be? Let's think about it. So we know that alpha, let's see, if we go from 0 to 2 pi radians, that'll be 1 full revolution. Same as with the pedal, like each circle is going to take 2.2 pi radians to rotate because it's all relative. Even though the radius lengths are different, because a radian is defined in terms of the number of radius lengths subtended, we're going to get the same interval. But if we talk about the tire valve in terms of theta, then it'll be slightly different. Notice that alpha is equal to 4 theta. That means that theta is equal to alpha over 4. And so if it takes us 2 pi radians to do 1 full revolution, then it'll take pi over 2 radians in terms of theta. Let me try to state that again. As theta goes from 0 to pi over 2, and since alpha is 4 times theta, well, pi over 2 times 4, that gives us 2 pi, a full revolution. So if we just turn our pedal pi over 2 radians, the entire tire valve goes around 1 complete revolution. Let's see, graph F and G. I don't even remember writing F and G. Graph F and G on the same set of axes below. Okay, so F is, f of theta is cosine theta. Okay. And then there's g of theta, cosine of 4 theta. So notice the difference here is that the periods are different. In terms of theta, like if we say that the x-axis is theta, then the period for G is smaller than the period for F, I believe. So this would be theta in radians, and then the output is horizontal distance from the center of each circle. Let's see, let's just go like this is pi over 2, this is pi, 3 pi over 2, and 2 pi. So we know that the horizontal distance, let's say this is 1. For that pedal, we start at 1, go down to pi over 2, and then 1, 2, 3, 4, here's negative 1. The function's going to look like this, and it's going to repeat. Let's see. something like that. And now the other function, g of theta, which is equal to cosine of 4 theta. Its period is different. Its period is 2 pi over 4, or just pi over 2. So even though we start, if this is again the horizontal distance in radius lengths, radii is the units here. We're going to start 1 radii length. That's the distance the tire valve will be from the center of its circle. And then it's going to have 1 full complete revolution within this very small interval of pi over 2. This is going to be pretty crazy. I don't even think I'm going to be able to graph this, but like it's going to go down here, come up. No, I can't do it. Let's see. We're going to have to wind up back where we started at pi over 2. So notice that here, like this was a full period, like this yellow distance here. From here to pink distance, from here to here. That's 1 full period. We have to squeeze that in this little bitty space here. Something like that. This thing goes, should be periodic, should be equal distances there. Not very easy to draw. So we really need to make our scale much bigger to draw this accurately, but we can see that even though we're turning our pedal and it's moving at a, that's the green function, it's moving at its rate, the tire rotates much quicker. So what is the period of f? The period of f, it repeats after 2 pi units. The period of g is pi over 2. It repeats after pi over 2 units. So explain what the period of g means in the context of the pedal and the tire of the valve. So as the tire valve rotates 1 complete revolution, the pedal only rotates 1/4 of a revolution. Because the pedal is only sweeping out pi over 2, that's 1/4 of the entire revolution. But that makes the tire go around an entire revolution. The tire valve always sweeps at an angle 4 times greater than the pedal. Explain why the period of g is less than the period of f. Well, let's see. In 1 cycle of the pedal, the tire valve makes 4 cycles. So the tire valve cycle length, that is the period, must be 1/4 the pedal cycle length. Suppose the bike technician changes gears on the same bike described in question 4, so that the wheel has a different rate of rotation relative to the pedal rotation. Okay, Consider the function h defined by h of theta equals 12.5 cosine of theta over 2 that defines the horizontal distance of the tire valve on the wheel from the vertical axes in terms of the pedal angle theta, swept out counterclockwise from the 3 o'clock position. What does the quantity theta over 2 represent in the above definition of h? Well, basically, it represents the angle that the tire valve sweeps out. So, because h is that horizontal distance, notice we're multiplying by 12.5. We're going to have actual units of inches here. And so the input of our function cosine must be the angle the tire valve sweeps out. Notice that it must be half of what the pedal angle sweeps out. What interval of the quantity theta over 2 results in one full cycle output of the values for the function h? So we know that we're going to have one full cycle for 2 pi radians. And let's see. So I think that's the answer. This has to sweep through 2 pi radians for there to be one full cycle. Use your answer in part B to find the interval of theta that results in one full cycle of output values of h of theta. Okay. So I think that we need to take our 2 pi radians and divide it in half to get 4 pi radians. That's what my intuition tells me. Let's see, because this is how the book did it. They just had this. Theta over 2 needs to be 2 pi. So if we multiply by 4 on both sides, we'll see that theta equals 4 pi. So if theta sweeps out 4 pi radians, that results in one full cycle of output values for h of theta. So this time, it takes it like the pedal, it takes us, like the tire moves faster than the pedal. Actually slower than the pedal this time. We have to roll 2 complete revolutions to get 1 revolution of the tire valve. Which of the answers above, B or C, is the period of h? I think the period of h is 4 pi. I remember that period is always just 2 pi over b, where b is the coefficient of the theta term. Let's see, the textbook says the period of h is 4 pi since it is the interval of theta required for h to result in one full cycle of output values. So when the pedal rotates 4 pi radians, the tire valve will rotate 2 pi radians, or 1 period. Describe what the output quantity of h of theta represents. Well, h of theta is the horizontal distance from the wheel's vertical diameter of the tire valve in inches. Notice it's again in inches because we're multiplying by the radius, 12.5, because this cosine value only gives us the portion of the radius. So if we multiply that by the radius, we get the horizontal distance in inches. The function h is defined by h of theta equals sine of 4 theta plus 2, where theta is an angle measure in radians. Complete the following table. Let's see, sine of 0 is 0, plus 2 is 2. Sine of 4 times pi over 8, well, 4 times pi over 8 is pi over 2. And I know that sine of pi over 2 is 1, plus 2 is 3. Let's see, 4 times pi over 4 is pi. Sine of pi is 0, plus 2 is 2. Maybe I should demonstrate the next one with a hand calculation here. H of 3 pi over 8 will be sine of 4 times 3 pi over 8 plus 2. This simplifies as sine of 12 pi over 8, or sine of 3 pi over 2 plus 2. And on the unit circle, 3 pi over 2, that's just this angle right here. So we want this point, which is the radius length would be -1, plus 2 equals 1. So this would be 1. And sine of 4 times pi over 2 would be sine of 2 pi, which would be 0, plus 2 would be 2. And then 5 pi over 8, let's see, that would be 5 pi over 2, which would just be the same as pi over 2. It's on the circle. If we start here, we go around, there's 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2 is just like sine of 5 pi over 2 is the same as sine of pi over 2. So this would be 1 plus 2 would be 3. Then sine of 4 times 3 pi over 4 would just be sine of 3 pi, which would be 0, plus 2 is 2. And now we need to graph this. I'm going to use a little bit of space this time. We'll say this is pi over 8 here. We'll go 3 more tick marks, and this will be pi over 4. 3 more. 3 pi over 8. Notice that we're just adding an eighth each time. If we add another 8, we'll get to 4 pi over 8, which is pi over 2. And then 5 pi over 8 and 3 pi over 4. You should note that each of these are 1 pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8. And then let's just say this is 1, this is 2, and this is 3. So at 0, we're at 2. At pi over 8, we're at 3. At pi over 4, we're at 2. Then 1, 2, 3, and 2. I feel like that's the best computer graph I've made all semester. Okay, what I notice here is that this is the graph of the sine function, but there's a vertical shift. Adding that plus 2 has shifted the graph up 2. So this is like this line y equals 2 is sort of like the center of our graph. I know that has some other name. Don't remember what that is though. So let's see what the questions are. What is the period of h? What does the period of h represent? So notice how long it took before we started repeating. What's the change in input values before we repeat? We go from this point to this point. That's one complete revolution. and you see that that's from 0 to pi over 2, so the period is pi over 2. And what does this represent? Let's go look at our function one more time. So we just have a function h. It doesn't really tell us what the output represents, but because it's sine of 4 theta plus 2, so you might have had a lot of your own interesting observations, but I just noticed as theta varies from 0 to pi over, did I say pi over 2? Yeah, pi over 2. The output of h makes a full cycle. What is the amplitude of h? The amplitude is the vertical distance from this line that I've called the center. So here is basically the center. And this vertical distance is the amplitude. That's 1 unit. You can see it's the same here. 1 unit. So the amplitude is 1. Okay, not really sure why they're asking you about the amplitude since we haven't defined amplitude yet. This is from the book. In general, the amplitude of the function y equals a sine of theta is the absolute value of a. So that's what we have here. We have just a sine of theta, and the amplitude would be 1 because that's the coefficient of sine here. And this is from a packet of stuff I made for you guys, like essential things from chapter 7 and 8. You might want to ask me about that. I can give you that packet. Okay, let j of theta equal sine of theta over 2. Since the argument to the sine function, theta over 2 in this case, always creates a full cycle of output values every 2 pi radians, how does theta vary as the argument to the sine function, theta over 2, varies by 2 pi? So I want to try to make sense of this last statement. Theta over 2 varies by 2 pi. Essentially what this means is if we have some final value, theta final over 2, well, that's not a good way to put it. Let's just call theta over 2x for a moment. And we want it to vary, meaning it's got to change by 2 pi. Now if delta x changes by 2 pi, it basically means that we had some final value of theta over 2 minus some initial value of theta over 2, and that equals 2 pi. Or notice if we multiply each side by 2 here, we'll get 4 pi equals theta final minus theta initial, or 4 pi equals the change in theta. So how does theta vary? It changes it by 2 pi. So as, I don't know if I just said that right, as theta over 2 varies by 2 pi, theta varies by 4 pi. The book uses the language argument to refer to this part inside of the sine function, and the input is theta. I'm not sure if it'll be helpful to use those terms, but I might use them. Given the functions f and j are defined as f of theta equals sine of theta and j of theta equals sine of theta over 2, construct graphs of f and j on the same axis. Yay! So let's say that the horizontal axis is the angle measure theta in radians, and the vertical axis is just radii, which is the output of the sine function. And so I'm just going to mark this like, let's see, pi over 4, 2 pi over 4, or pi over 2, 3 pi over 4, 4 pi over 4, or pi, 5 pi over 4, 6 pi over 4, which is the same as 3 pi over 2, 7 pi over 4, and then right on the end here this will be 2 pi. And I'm just going to put, let's see, 1, 2, 3, 4. Yeah, I'll just make this 1. Okay, so sine of theta, I'll make this one, I don't know, blue. Sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And sine of 2 pi is 0. So I sort of skipped those pi over 4 values. They, I just thought that we would use those, but I might be wrong. I probably should have counted off by 2 pi's or something, but here is our function. So there's one full period of the sine function. Now, let me try j of theta equals sine of theta over 2. So it'll start at 0. Let's see, what happens at sine of pi over 4? We get sine of pi over 8. So I didn't really mean to do this. Let's see. I really should have went in 2 pi's, but let's try this one. Sine of pi over 2. That's going to be 1. So notice that this one doesn't make it up to 1 until way over here at pi. And it doesn't get back to 0 until we go to theta is 2 pi, because 2 pi over 2 is pi. So my graph isn't very good because my scale isn't perfect. But we're going to go up to 1, come down to 0, and this one's going to have a much larger period. Remember, it's going to have a period of 4 pi. Because this is only half of the shape. Notice here that the first hump goes to pi, and then the second bottom hump goes to 2 pi. So one hump is half of a period. That's what we have here. Half of j's period is shown, and that's 2 pi. So the full period is 4 pi. So I think I just explained how I determined the period of j, and I can't really identify the period of j on the graph. I don't think so, because I don't have the full graph of j. But maybe you guys have some better graphs of this. Make the scale smaller. So this should be like pi over 2 right here, pi, 3 pi over 2, 2 pi. If we did that, we'd get a better picture. So that 4 pi was the last one. Let k of theta equal 2 sine of 3/7 theta plus 5. What is the period of k? Explain. So the quick and easy way to find the period is if this is the amplitude sine of b theta plus k. A is the amplitude, b, 2 pi over b is always equal to the period. K is the vertical shift. So we have our period is equal to 2 pi over 3/7, which is 2 pi times 7/3, which is 14 pi over 3. Okay, so this output will complete a cycle of values after the input varies by 14 pi over 3. Consider the graph of the function h below. What is the approximate value of the period of h? Let's see. Here I start, and then I make one full revolution to over here, so it looks like about 2.1. The book's answer is 2 pi over 3, which is equal to about 2.1. I'm not sure how they got 2 pi over 3 from that graph. Maybe because here's 6.28, which is 2 pi, and so we go through 1, 2, 3 complete revolutions before we get to 2 pi, so 2 pi over 3 would be the period. What is the approximate value of the amplitude of h? We just need this vertical distance here from the horizontal center to the tip top, which is 2, about 2.5. You can notice that that's the same distance from this horizontal line down to the very bottom of the graph. Define a formula for the function h. Let's see, h of theta equals the amplitude and sine of, we need to find our b. Remember that the period, capital T, is equal to 2 pi over b. So b is equal to 2 pi divided by the period. So 2 pi divided by 2.1, or you could use this value, 2 pi over 3, a little bit more exact. And so we'd get 3. And so, let's see, we could just put 3 theta here. Since the graph actually had x on the x-axis, we really should put 2.5 sine of 3x. Note that I knew it was the sine function because it went right through the origin. If it was the cosine function, it would have started on the vertical axis, because the horizontal distance would be 1 radii. Okay, moving on to number 10. A picture of a water wheel used for power in the 18th century is illustrated below. The bucket starts here, and radius is 11 feet. Bottom of the wheel is 2 feet above the water line. Sketch a graph of the height of the bucket above the water in feet as a function of the angle of rotation, measured in radians of the bucket from the 3 o'clock position. Okay, so angle of rotation, that would be theta in radians here. The height of the bucket above the water in feet will be the vertical axis. Alright, notice that we begin at a distance of 13 feet, or 11 plus 2 feet above. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me just count by twos. 2, 4, 6, 8, 10. So we start at 11 feet high. Then when we get to this point, will be 11 plus 11 plus 2, or 23 feet high. And that's it when theta is pi over 2. 23 feet high. Let's see, 12, 14, 16, 18, 20, 22, 24. I'm going to go way up off the graph right here. And then when we get to pi, right here, we'll have 13 feet again. Oops, I totally did not do that right. Back up a little bit. The first one should be 13 feet, because we weren't just 11 feet high, we're 11 plus 2, 13. Then when we go to pi over 2, we'll be at 20. Let's see, 11 plus 11 is 22 plus 2, 24 feet is where this should be. Sorry. Okay. Then let's see what happens when we're at pi. So 1, 2, 3, 4, here's pi. When we rotate from here to here, we're 13 feet high once again. And then when we get down to 3 pi over 2, we're at only 2 feet off the ground. So I'm going to go 3 pi over 2 right here. We're 2 feet off of the ground. Then when we get to 2 pi, that's one complete revolution, we'll be at 13 feet. And then if we went, we just keep going. I think we can trace this. There's one full period right here, and then it'll just keep repeating. Define a function f that represents the bucket's distance d in feet as a function of the angle of rotation measured in radians of the bucket from the 3 o'clock position. Well, we start off 2 feet above the ground. I think, hold on a second, let's take a look at this. You know, we start off really, our initial position is 13 feet above the ground, plus our amplitude here will be 11. Notice 23 minus 13, or 24 minus 13 is 11. That's just the radius is our amplitude. So I'll just have my radius here, 11 times sine of theta. I think that should work. Because notice that this is just our sine of theta is the percentage of the radius that we are, the height, times 11. That gives us the actual units, like feet, plus we're starting 13 feet high. Define a function g that represents the bucket's distance d above the water in feet as a function of the number of feet the bucket has rotated counterclockwise. So notice that our angle theta, we can write that in terms of the number of feet, because we know that theta equals the arc length divided by the radius, which is the number of feet rotated counterclockwise divided by our radius, which is 11. So s over 11. We can say that our function is g of s, which is 13 plus 11 sine of s over 11, and this is multiplied here. Thanks for watching.